Alright, this is the chemistry video for combined gas law. We've learned at this point PV equals nRT, the ideal gas law. We saw in that video how to rearrange it to solve for our R constant. So if I divided both sides by N and T, we're going to get PV over NT is equal to R. Well, we know that R, this value right here, is a constant. It doesn't change. For any scenarios of pressure, volume, and temperature, a number of moles, we get R. Well, if we change any of those situations, a pressure, a volume, a temperature, or a number of moles, it still ends up having to equal R. So we can rearrange and create a new formula that says P1V1 over N1T1 is equal to P2V2 over N2T2. In other words, a set of conditions before must equal a new set of conditions because they both have to go through R. So that is essentially the start of 13b, the combined gas law. P1 times V1 over N1T1 equals P2 V2 over N2 T2. In other words, your set of initial conditions, your starting conditions, must equal your set of final conditions. Unlike PV equals nRT, where your units were very, very specific, this time, with the combined gas law, you can use pretty much any units you want for pressure, volume, or number of moles. Well, it always needs to be number of moles. The only one that still has a requirement is that Kelvin must be your unit for temperature. Remember, we're using that scale in order to avoid potentially trying to divide by 0. So temperature must be in Kelvin, but everything else can be any units you want as long as they match before and after. So your temperature, if you start in atmospheres, must end in atmospheres. If I give you one of the units in atmospheres and the other one in millimeters of mercury, you need to convert one to match the other one. It doesn't matter which one you convert to. So you could convert your atmospheres to kPa, to millimeters of mercury, or your millimeters of mercury to atmospheres. It literally doesn't matter as long as they match. So, example 1 says that if I start with a 5 mole sample of gas and it takes up 4.3 liters at STP, so standard temperature and pressure, then I add 3 more moles of gas, I have an increase in volume and an increase in pressure. What is the final temperature that results? Well, I have 2 sets of conditions, right? I have an initial starting set of 5 moles. So here would be my N1. I'm going to move it down so I can mark a little bit. I got an N1, a starting number of moles, a V1, a starting temperature, a starting volume, and I know that it's an STP, which is my P1 and my T1. There we go. Hang on. There we go. T1. It's a weird T, but deal with it. So N1, V1, P1, and T1, so a starting set of conditions. I then start writing new conditions. 3 more moles of gas. Well, that becomes my N2. My volume increasing to 5.44 liters. Well, there's my V2. Pressure going up to 5 atmospheres. That's my P2. And I want to know my final T2. I'm going to go ahead and let all of this information pop up on the screen in a little bit more of an organized fashion. So don't be surprised here in a second when all of this information pops up on the screen. And maybe that's a good way that you're going to want to organize it when you attempt these problems. All right, so here's all that information organized a little bit better. You can see on the left side we have all of our conditions, our starting number of moles, our temperature and pressure STP, 0 degrees Celsius, which we've converted to 273 Kelvin. A pressure of 1 atmosphere and a starting volume of 4.35. And then on the right we have our ending conditions. We added 3 more moles of gas, so we have a total of 8 moles. We're looking for a temperature. I increase my pressure to 5.25 atmospheres and I have a final volume of 5.44 liters. So I can go to my new formula, which we call the combined gas law, P1 V1 over N1 T1 equals P2 V2 over N2 T2. And we can either plug all of our numbers in now and rearrange, or we can rearrange everything and then plug in our numbers. Again, if you've been watching any videos that I've made, you'll see that I prefer to rearrange all my information first. So we're going to solve so that we get T2 not only on the top of our equation, but also by itself. So we're going to multiply this side by T2 so that we can get T2 on the correct side of my division line. So it pops up off the bottom on that side and onto the top on the left. So I get T2 times P1 times V1 over N1 T1 equals P2 V2 over N2. And now I can isolate T. Now that I got T2 at least on the correct side of my equation and on the top, I can use a little bit of algebra to move all of my 1's to the other side. So I can multiply both sides by N1 T1, divide both sides by P1 V1, and I end up with T2 equals P2 times V2 times N1 times T1 over N2 times P1 times V1, right? So we did some algebra. We multiplied both sides by N1 T1. Whoops, that switched to yellow there for a second. N1 T1, so it canceled out over there and moved over here. And then I divided both sides by P1 V1, so it got rid of it on the left and made it pop up on the right. At this point, it really does turn into a plug and shove problem. You're going to plug in all of this information on the top, whether it's a 1 or a 2, into the corresponding spots in that equation. So I'm going to pause the video here. I'm going to let you write all of that information in, and that all of those numbers will pop up here in just a second, and we can calculate the final answer. Alright, if you plug everything in correctly, if you've done your algebra correctly, you should end up with a final temperature of 1,120 Kelvin. It's a really, really big jump, but then again, we see some major increases in terms of pressure as well as number of moles. So we actually kind of we can see that jump. Essentially, as long as you can do the algebra, you're in great shape. If that algebra there, rearranging all those letters, was a little off-putting or kind of freaked you out, don't worry. You can plug in all of your numbers first. You can combine them so you have a lot less numbers running around, and then do your algebra. In fact, on the next example, that's probably what we're going to do. So on that note, example number 2, a 12.8 liter tank contains 63.996 grams of oxygen. The pressure in the tank is 635.1 kPa at 25 degrees Celsius. If this tank were to leak, lose 0.352 moles of oxygen, and the temperature decreases to 23 degrees Celsius, what would be the resulting pressure on the tank? So I'm going to, again, ask you to pause the video. I want to see if you, on your own, can kind of sort through all of this information, see if you can pull out all of your initial conditions, all of your final conditions, remembering something along the lines of the fact that N is equal to number of moles of gas. And I want to see if you can organize all this information so that we can more easily plug it into your formula. Alright, hopefully you're able to pull all of this information out. That we start with approximately 2 moles of gas, which we use our our mole conversion to go from grams to moles. So we start with 2 moles of gas. We start with an initial pressure of 635.1 kPa, which we do not have to necessarily convert because we're not using our R constant. We converted our temperature from 25 degrees Celsius to 298 Kelvin, and we start with a tank that is 12.8 liters full, or in volume. At the end of our changes, we have lost 0.352 moles of oxygen, so we've gone from 2 down to 1.648, subtracted away the moles that we lost. We're looking for our second pressure, which we're going to solve for and end with a unit of kPa, because we start with our units of kPa. We dropped to 23 degrees Celsius, which we've converted to 296 Kelvin, but the volume of the tank didn't change. It started as 12.8 liters, it's going to end as 12.8 liters, which means when we look at our combined gas law, our changes law, which is we're looking at a bunch of changes, P1V1 over N1T1 equals P2V2 over N2T2. V1 and V2 are the same value. So they're going to actually cancel each other out, and we don't even need to worry about plugging them in. Because those numbers are the same, they have no effect on our problem. So we're going to solve for P2. This time, in this example, I'm going to plug in all of my numbers and simplify before I do any algebra, just to kind of appease those of you who want to see that particular way done. Pause the video here, see if you can solve it on your own. All of the work will pop up here in about 5 or 6 seconds. So pause the video and check your work versus what's about to pop up on the screen. All right, so over on the right, you now see all that work pop up. We've plugged in all of our values first. We simplify the left side to be 1.066. We simplify the right side to be P2 over 490.77. We multiply both sides by 490.77 to get rid of it on the right. If we include all of our units in the work, you'll see that moles times kelvins get canceled out on both sides, and we end up solving to have 523.16 kPa as our final pressure. All right, here's example number 3. Same deal as both examples number 1 and 2. I want you to go ahead and stop the video here, take a few seconds, see if you can organize all of your information, and see if you can determine what your start conditions are and what your final conditions are so that we can apply our formula just that little bit easier. All right, so in this example here are our set of conditions. We're going to start with 295 degrees Kelvin, and we're going to try to figure out what that goes to. What is the new temperature? We have a starting pressure of 754 millimeters of mercury and end with 723 millimeters of mercury. Our units of pressure match, so no need to convert anything. We start with 15 liters. We end with 23 liters, so those units are good. But notice that I don't tell you anything about how much gas you start with. Here's the nice thing about these problems. If we don't tell you anything, a start or a finish, with any of our variables, you're allowed to assume that that variable doesn't change. So we can't assume that for temperature because we start with 295 and we know that there will be a change because I'm asking for a new temperature. But I don't give you a starting number of moles, I don't give you an ending number of moles. So you're allowed to assume that those numbers do not change, and so therefore they're not going to make it into our P1V1 over N1T1 formula. So I'll write the full thing just so we can see it. P1V1 over N1T1 equals P2V2 over N2T2. We're assuming our number of moles don't change, but we're going to solve this for T2 once again. Be careful because, again, you're solving for a temperature in the bottom in your denominator, so you have to get it out first before you solve for it. Pause the video here, see if you can solve this problem on your own. In about 5 or 6 seconds, all of the work will pop up and you can check all of your work as well as your final answer. All right, we rearranged for T2, as you can see over there on the bottom. We plugged in for T2, we plugged in our P2, V2, T1, P1, and V1, and we solve and we can round a little bit. We try to shoot for the correct number of sig figs. All of our numbers have 3, so our final answer should have 3. And they end with an approximate T2 of 434 Kelvin. All right, last example problem. Hopefully you kind of have a good grasp here. We're going to go ahead and pause the video here, just like we have done for the last few examples, except this time not only will the set of conditions pop up, but also all of the work and all of the final answer is actually going to pop up as well. So pause here, spend the next few minutes organizing all your information, seeing what you need and what you don't need, and see if you can solve the entire problem on your own. If you can't, that's okay. Follow along till you get stuck, and then play the video. All of the work will pop up with the final answer as well as some explanation of how we got there. All right, here is all of that work for solving this problem. We have our set of conditions, volumes, temperatures, and pressures. Just like in that last example, we don't give you any number of moles or how much gas, so you're allowed to assume that it doesn't change, which means we can look at our P1V1 over N1T1 formula, cross out our n's on both sides, that way because they cancel each other out. You can rearrange to solve for our new volume, V2, by multiplying each side by T2, dividing each side by P2, and then from there you plug and chug. Now, I didn't put all of my units in the work. We highly recommend that you do. Our pressure would be in atmospheres. Our our volume would start in liters. Our temperature is in Kelvin. Our P2, our second pressure, is also in ATMs. And our T1, our starting temperature, is in kelvins. And when you include all your units in the work, you actually see which ones cancel out so that we're left with liters. And sure enough, liters is the unit that we want because we're solving for volume. Hopefully you have a pretty good understanding of all these this different formula that really isn't a new formula. You got PV equals nRT. This is just a variant of that formula. Really practice if you want to get good at these. Practice pulling out all of these numbers, identifying what they all are, and looking at their units before you start, and it's really going to help you save some time. Remember to feel free to come in and see us if you need some help. Identifying or just doing the algebra, and we'll be happy to kind of walk you through some more example problems and explain anything that we need to.